This is an example of using Microsoft Excel to calculate air buoyancy corrections for quantitative mass measurements in a chemistry laboratory. So as we discussed in lab, the buoyancy of air results in a observed net mass on the balance, which is lighter if the object has a density less than the density of the weights, in this case 8 grams per centimeter cubed, and it will give it a negative error if the density of the object is more than the density of the weights. So this relationship is described by the true mass is equal to the mass observed, 1 minus density of air over density of the steel weights, divided by 1 mass the density of air divided by the density of the object. And the density of air is equal to this relationship defined in terms of barometric pressure, vapor pressure, and temperature in degrees Kelvin. Now, these equations are very straightforward but tedious if you had to do them by hand on your calculator. So Excel gives us a nice tool for doing this, and this example also gives you a brief introduction to some topics in Microsoft Excel. So I like to begin my spreadsheets with my name, date, a title for the calculation, and this is helpful in terms of keeping yourself organized. Notice that this worksheet is listed below, and it's often in a class like this helpful not to save these each as different workbooks, but to actually tag these all onto one workbook as a series of multiple worksheets. And that's just a good organizational idea. Okay, so these are the relationships we want to use. Let's go see how we would implement this in Excel. We'll start with some labels. It's helpful to put the units on each of these inputs, and I've designated the inputs in yellow boxes. So we're going to start with a measured mass of 3 grams. That's what the mass displayed on the analytical balance would be. We measured this mass at 25 degrees because that was the temperature of the laboratory. They're inputs, so you would just enter these values from your laboratory notebook. Temperature in this case in Kelvin is 273.15 plus C15. So this is a computed value. Notice that it's not yellow. Barometric pressure in torr, or millimeters of mercury, 760. Relative humidity. Typical lab environment, you'd have about 70% relative humidity. You can play around with that. We have a way to measure that, but you can also put in different relative humidities and see how much of an effect it has in our final computed mass. So we're going to use 70%. Notice the units here. So vapor pressure of water. Vapor pressure of water is the saturation vapor pressure of water at 25 degrees times 0.7. So there we go. Equals 23.76. That is the saturation vapor pressure of water at 25 degrees. C18 is the 70 divided by 100. That gives me a fraction of 0.7. So 0.7 of 23.76 is 16. This Wikipedia link would take you to the saturation vapor pressure of water at different temperatures. So if you were working in a cold room or in a very hot environment, you might want to correct the saturation vapor pressure for the actual temperature of your room. Okay, now we get on to the density of the air. Density of air is a computed value. And you'll notice that this equation and this equation align. So here's my 0.46468 coefficient. C17 is the barometric pressure, minus 0.3783 times C19, the vapor pressure, divided by C16, which is the temperature in degrees Kelvin, and this 1,000 is because this density equation is in units of grams per liter, or grams per 1,000 centimeters cubed, and we want the density of all of our objects to have the same unit so that this term in the air buoyancy correction becomes dimensionless. And so the divide by 1,000 gives us the density of air in grams per centimeter cubed. And you'll notice this is small. So this is a good check value. When you build your own spreadsheet, you should get 0.00117468 as the density of air. And if you don't, you've made an error in your equation. Okay, density of the sample. Density of sample is an input. You need to know the density of the sample, and we'll see that the density of sample has a influence on the air buoyancy correction, as you would expect from this relationship. There it is, ds. Okay, density of the weights is 8. All of our analytical balances use 8 grams per centimeter cubed stainless steel weights. So, down to the final result, 3.03 is the computed true mass. So here's my relationship. C13, measured mass, 1 minus $C20, that is the density of the air. $C, $22, that is the density of the steel. 1 minus C20, again, density of the air, and C21 is the density of the sample. So the actual density of the sample is 3.00309, and so that basically means that for a density of 1, or very close to 1, you get about a 0.1% error in the mass measurement. Now, this is a good thing to pay attention to. If in your analytical work you're only making measurements to 1%, then 0.1% is clearly 10 times less. And so air buoyancy corrections aren't important. The error in not making this correction is insignificant at the 1% level. And that's why we didn't worry about this in general chemistry. However, if you're trying to make measurements at the 0.1% level, then you need to pay attention to air buoyancy and you should apply the appropriate correction. As an analyst, it's your job to understand when you need to make these corrections and when you don't. Now, as a further example, I'm going to scroll down and I'm going to look at the actual errors in a 2-gram mass as a function of different densities. So this is going to be objects with a very low density. This is the object with the same density as the steel, and this would be objects with high densities. So now this is my buoyancy correction, and what I've done here is I've used the C $20. These are what are called absolute addresses. These are referring to the densities further up in my spreadsheet, and I don't want these to change. This is the density of air, the density of steel, the density of air. Those are all constants. But what I do want to change is this A29, the density of the object. So you notice there's no dollar signs in front of the A29, and that means it's a relative address. Notice if I click on the next cell down, it's A30 and A31. So if you put dollar signs in front of the addresses, you get absolute positions in your spreadsheet. And if you don't, you get relative positions. And if you have a dollar sign in front of the A, it would fix the A as an absolute column address, but the 31 would increment up as a row address. Similarly, if you put the dollar sign in front of the 31, you'd fix the row, but allow the column to float. And you can toggle these dollar signs on and off using the Apple T key on a Mac or F4 on a PC. So that's what I did. I went down and filled all these in. You can see now I'm down to A36. I calculated the corrected mass, and then I went in here and I said, well, it should be, here's my corrected mass minus what it should be 2, or what was observed. And this is the error if I didn't apply air buoyancy. And you can see with a density of 0.1, we get about a 1% error. Okay, so for objects with very low density, you can get a pretty large error. As we approach 1, the density, the error becomes, again, 0.1%. It becomes exceedingly small as we approach 8. And of course, at 8, there is no error in the mass measurement because the buoyancy effects are equal for both the steel balance weights and the object. And then if your object is greater than 8, you actually get a negative error because your true mass is now less than the observed mass because the buoyancy on the steel weights is now greater than the buoyancy on your sample. Okay, so this is an example of how to do an air buoyancy correction, how you might be able to generate a table to understand this, relationship as a function of density using absolute and relative addressing. And if we come over here, I can now make a plot. And so this is the error in buoyancy as a function of density. And you can see it starts out large and rapidly decreases. And this is the same thing on an expanded scale, focusing on the region between 4 and 10. And again, the errors are small, passes through 0, and then becomes negative on the back side. So That's our first example in Excel, doing air buoyancy corrections for the analytical balance.